Hello and welcome to Do Try This at Home, brought to you by the Institute of Physics. This is an experiment I call hot water rising, a beautiful way to talk about temperature with your family. The first thing that you're going to need are 4 bottles that are see-through. They can be glass or plastic. The next thing is some cold water from your cold tap and some hot water from your hot tap. You're going to need some food colouring to colour my water, some teaspoons to mix it in, something to get that water to the bottom of your bottles. I am using half a turkey baster, a tray to catch some drips, and you're going to need a couple of pieces of thin cardboard as well. Choose a colour for your hot water and one for your cold water. I'm going to go with yellow for my hot and blue for my cold. And then you just want to mix them in. Let's start off with my cold water. There we go. I'm going to do exactly the same with my hot water. The next thing is to fill up 2 bottles with your cold water and 2 bottles with your hot water. Ah. I made such a mess. There we go. There's 1. You want to get the bottles as full as possible. And now we're going to do exactly the same with hot water as well. Take a bottle of hot and a bottle of cold. Take your pieces of cardboard, put it on top, and then flip the bottle over, holding the cardboard on top, and balance it on top of the cold water. There we go. Is that balanced? So now we are ready to start the experiment. Sam, can I borrow you for a moment? If I hold these steady, can you slide this little bit of cardboard out of the way? There we go. So if I hold and you slide. Right. Yeah. And then same on this side. Perfect. Where the hot water was on the bottom and the cold water was on top, the bottles have now almost completely mixed. On the other side, where we've got the cold water on the bottom and the warm water on top, they've stayed in perfect layers. But what's going on here? We've discovered that hot water floats, just like a cork will float to the top of water. The cork floats because it is less dense than water. Now, everything is made of molecules, and density tells you how squished those molecules are together. The more dense something is, the more that they're squished. Cork is less dense than water because there are loads of tiny gaps in there filled with air, which is why it floats and rises to the top. But what about a material that's the same, made of the same molecules, like the water in my experiment? If we could zoom in on those molecules of H2O, we would be able to see them jiggle and move. Now, temperature is a measure of how fast those molecules are jiggling and moving. The higher the temperature, the quicker they go. In hot water, those molecules are jostling each other, they're moving around, and they end up, on average, further apart than in my cold. If we had exactly the same amount of water, there'll be more molecules in my cold water than in my hot water. My cold water is more dense. On this side, I put my hot water, something less dense, on the bottom, and my cold water, something more dense, on top. We know from my cork experiment that this can't last, and so the hot water rises up through the cold, and the two have mixed together. There's a special word in physics for this called convection. On the other side, we've got something more dense on the bottom, something less dense on top. There's no convection there, and my water has stayed in perfect layers. This was hot water rising, and see you next time. Nobody got wet? Hey!
If you take your coffee black, you're likely missing out on one of the most curious displays in fluid dynamics. Though well known to science as delayed coalescence, this phenomenon is poorly understood. Now, researchers from MIT have discovered how and why it occurs, and the results could help scientists understand important fluid dynamic effects that lie beyond their morning cup of joe. Since the 1960s, researchers studying coalescence have examined the roles played by properties like density, surface tension, viscosity, and surface charge. Early on, it was discovered that drops levitating on a fluid bath actually rest on a cushion of air, but it remained unclear just how long that air cushion could be sustained before collapsing under the weight of the drop. To address that problem, the MIT researchers focused on one often overlooked property: temperature. Specifically, the temperature difference between a drop and a fluid bath. Using a high-speed camera and silicone oil as their medium, they discovered that drops immediately collapse only below a critical difference in temperature. Above that value, drops tend to linger. What's more, the team discovered that the amount of time the drops remain suspended scales with the difference in temperature. The bigger the difference, the longer the drops delay their plunge. A combination of mathematical modeling and experiments provided a closer look at the crucial role played by temperature. The temperature difference between a cold drop and a hot bath creates flows both in the drop and the air cushion that increase the pressure in the cushion. That high pressure helps support the weight of the drop. The result is an air cushion that is sustained until the drop and bath reach nearly the same temperature. The researchers' model closely approximates the delay times observed in the lab, and their results could one day inform many important natural and industrial processes involving droplet interactions. Those include the formation of raindrops in clouds and the dynamics of emulsions, which are used widely throughout the cosmetics industry. In the meantime, when ordering your next cup of coffee, be sure to ask for cream and hope to catch a glimpse of this fascinating physics in action.
For this, you will need a balloon, a plastic bottle, a bendable straw, glue and a pair of scissors. Make a hole near the mouth of the plastic bottle with scissors. Insert a straw in the bottle and secure the hole with help of glue. Fill the bottle with water. Now blow a balloon and hold the neck with fingertips. Carefully fix the balloon on the mouth of the bottle. When you release the air from the balloon, it creates pressure in the bottle and thus pushes water out, creating a wonderful water fountain. So, let's look at what actually happens in this experiment. The air inside the balloon is under higher pressure. When you place the inflated balloon on the mouth of the bottle, the air pressure on the top of the bottle increases. This pushes down on the water in the bottle, which rises through the straw and comes out, making a little fountain. Instead of a single straw, you can also fix 5 straws in the bottle. You can fill the water in the bottle and fixed an inflated balloon. You'll see an elegant fountain with 5 streams. Make your own pressure fountain and have fun.
The bottle turbine is an amazing toy. It was designed by Durga, a school student. All you need to do is to mount a freely moving turbine on a bottle lid. Here you can see this. There is a white straw in the middle for the air to come out. There is the card sheet turbine which is mounted on a flexi wire. If you blow through the lid, air would come out and the turbine would rotate very smoothly. Now you fix the lid to the bottle mouth. This is the whole assembly. And now you stand the bottle upright and squeeze it repeatedly. Air would be expelled from the white straw and it would spin the turbine. It's a very, very enjoyable game. Next, you cut the base of this green bottle and repeatedly move it up and down in a larger bottle filled with water. As you move the green bottle down, air would be expelled out from the white straw and this would once again make the turbine spin. What a glorious toy. In the end, you just need to release the green bottle. It will sink down, air would be expelled and the turbine will spin. See this again.
You can do this amazing trick of making this top follow a path on this sheet. Notice it will go all along this path. Magnetic top. And to make this, you need a ping pong ball, steel wire, sellotape, cycle spoke, glue and some aluminum sheet. Now this ring magnet sticks to the cycle spoke, which is made of iron, but not to the aluminum sheet. And that's the basic principle. First cut this ping pong ball into 2 equal parts. Stick a ring magnet inside this ping pong ball and that makes our top. To decorate the top, put some glue on the edges of the top and stick this Newton's disc, which is basically a circle divided in 7 equal parts, all colored with 7 colors of light. And now, if you put this on a spoke, a cycle spoke, you can see the Newton's disc or this top going up and down magically without falling, spinning and going forward. Very amazing toy. And now to this next part of the trick. Take this aluminum sheet and make a broad curve with a GI wire. Galvanized iron, so it will stick to the magnet. stick this iron on the sheet with the tape. And you will see that the magnet is actually attracted to the GI wire but not to the sheet. And our trick is almost ready. When you put this top on the sheet, it just follows the path. Your friends don't know that there is a GI wire sitting at the back of the sheet and inside the top there is a magnet. You can make 2 of these tops and then have fun going around this loop. A simple magical trick with magnets. See how children are having fun? Spinning the top around the spoke and around the sheet. Hope you enjoyed it.
धीरे धीरे खड़ा हो जाओ, खड़ा हो जाओ. Take this like this. Fill the weight. Now put it inside water, not fully. Just rim should be up. Do you feel the same weight?
No, less.
Upper, you take it up. You feel the weight. Is it more or less?
More.
Go to down.
It is less.
It is less. Okay, take it out. You want to feel it?
Yes.
Do it. खड़ा हो जाओ. Now feel the weight. Now go down. Same weight.
No.
Inside water?
Inside water is feel lighter.
Lighter. Acha, I am holding it.
Yes.
Do you feel weight? No, no, you hold it also. Do you feel weight?
No.
Why you not feel?
Because you are not
Because
applying
I am applying a force.
force.
So, in this case why you feel less weight? In this case why you feel less weight? Water
Also
applying a force in which direction?
in upward direction.
Upward direction. Is it so? I have not told you. You feel that when you are inside water, the weight has become less.
Yes.
It can only happen as I gave a force in the upward direction. Okay, nice. ये क्या है? These are 3 medicine bottles. What are the properties? Are they equal or something?
Equal.
Volume?
Volume also.
Volume also equal. Now you see, what I have done? I throw it up. Why it goes up?
Because you apply force.
Because I applied a force. Now you see carefully. I am pushing it down.
Yes.
Then I am just releasing. Carefully see it.
Yes.
Who pushes it up?
Water.
Water. So that means water is giving a
Upward force.
upward force. Very good. And that upward force has a name. Like my name is B.N. Das. Like that, the upward force of the liquid, in this case it is water, but any liquid will have a upward force which is called buoyant force or buoyancy. You understand?
Yes. Buoyant force or buoyancy.
Have I said something or you understand this?
Understand.
You understood. Okay. Now, what I am going to do, that I am going to measure its weight. Okay, this is a stone, nice looking stone, and you have to tell me how many divisions this weight goes.
18.
18 division, and you also see
Yes. 18 days.
18 division. Now, if I pour it in water, if I place it within water, what will happen?
Water will apply upwards force.
तो इसका what will happen to its weight?
It will decrease.
तो see what is the weight? 12 or 11? Carefully देखो. Is it?
12.
12. Then 18 minus 12 is 6.
6.
Okay, ठीक है. So the buoyant force on this stone is 6 divisions. Okay. Now what I am going to do, I want to measure this force, whether there is something to do with that. So I completely fill this, and you see there is a beaker which does not have anything in it. So I completely fill up with water. It may not be completely filled. Why not? Acha, you have to look at it. I shall gradually drop by drop water, and when one drop falls out, you just, why it is taking water? Because of surface tension. 1 drop, 2 drop, 3 drop, still not gone down. Huh?
No.
Now?
No.
No. My God, how much water it is taking? Still not gone down, huh?
Yes.
It has become convex. Okay?
Yeah.
No drop gone out?
No. No.
Not yet?
No.
My God. Okay. So we can answer slight. Now what I am doing, I am going to place this inside that. What will happen? How much water will be displaced?
Extra water convex.
I mean by its weight or by its volume?
Volume.
Very good, very good. So I am putting it inside. Now I take it out. Take it out. So I take this also out and put it here. Now what I will do, I want to measure how much water it has displaced. So I poured this water here, slightly more water will be there, 1 or 2 drop. Now I am going to weigh this. Now you have to tell me very carefully. You will see later on. Let him see first. How much the upper surface? How much is this?
11.
11. Now you see. Oh, sorry.
11.
11. Now how to get the weight of the water? How to get?
By minusing the weight of that jar.
I am just pouring it. Now see the weight of the jar. 5,
4.
4.
4.
You see?
Yes, 4.
4. Then what is the weight of water? It was 11 minus 4,
7.
7. We got 6.
Yes.
But 1 or 2 drop extra has gone.
That's one.
So we can assume that the loss of weight of this equal to the weight of the displaced liquid.
Yes.
Again I am repeating that this body, when dipped in water, it lost 6 division weight, and the amount of water displaced by it, that weight is also 6 division. That means they are equal. And who has discovered that?
Archimedes.
Yeah, just below Archimedes. Archimedes, his king said that, can you measure the impurity in a crown? So when Archimedes at home, he got down in the bath, in a bathtub, and water came out. Immediately he started shouting, Eureka, Eureka, and without carrying anything, he ran to the king. I am not saying anything else. Okay? And this is Archimedes' principle, which says that whenever a body is partially or wholly dipped in a liquid, it loses a part of its weight, which is equal to the weight of the displaced liquid. So, here we have proved the Archimedes principle. Now you have understood that the amount of water displaced by this is equal to the buoyant force,
Yes.
the upward buoyant force, the 6th division.
Yes.
Now, if these are taken inside it, then it will be acted on by buoyant force
Yes.
and also the weight.
The weight.
So, I take any one of them, I dip it here. What you see? That is, it is completely immersed in
water.
water. See, carefully see.
Yes.
Do you see?
Yes.
That means it is neither going up nor going down. That means what does it mean?
Means buoyant force
And
and
weight?
weight are equal.
Equal. And then what happens? The body floats completely immersed in that. So, I take second body. I take the second body. What does it say?
It's wholly dipped in water.
Its weight is more than
buoyant force.
buoyant force. Then what happens?
Then
The body
dips in the
sinks.
sinks in the water.
Body sinks. Now, I take the third body. Now, the buoyant force is the weight of water displaced by it. When I release it, what happens?
It flows.
It floats. But one thing you must say me, that when it is here, then same buoyant force was acting when it is inside, because it has displaced the same volume of water. So, then what you say, the buoyant force is more when it is here, the buoyant force is more than its weight. That is why buoyant force pushes it up. Now, what you will say?
Now the weight is pushing it down.
The buoyant force has decreased because it has not displaced the whole volume of water, little bit less. So, now the weight and the buoyant force are
Equal.
equal, right. This is a problem in all the books. When they are talking about this floating body, they used to say body floats when buoyancy more than. It is not that. When it is inside water, then the buoyant force is more. But when it is floating like a ship,
Yes.
it floats like this. Okay. So, you understand that when it is inside it, buoyant force is more and weight is less. Therefore, the buoyant force pushes it up and it starts floating, and when it is stably floating on it, then we can say that the partial, this is, see, it is not immersed completely. So, this much is the buoyant force and the weight remains same. So, you get the idea of laws of floating body.
This simple toy demonstrates the flywheel beautifully, explaining the conservation of energy. Pull the thread and enjoy the rotational energy of dual fans or flywheels. You need a small box of metal or cardboard or even a matchstick box, some beads, wooden sticks, threads and blades made of card paper. Make 4 slits in the side of the box and insert wooden sticks inside so that they can rotate with little friction. Secure the sticks, inserting the beads, and then attach the card fan blades at the end. Now make 2 holes on the side of the board and weave the thread through one hole, once around each sticks and out the other hole. If you tighten the thread, both the sticks will move up in the slit. And now we are ready to have fun. Hold the thread tight, move the train and enjoy the rotating or moving flywheels. The moment you push the train, the thread causes these wheels to rotate. This is the concept of the flywheel. Another trick is to hold the thread up and let the box fall down. The falling box causes the wheel to spin wonderfully. So enjoy the dual flywheel just like these children.